So today we'll talk about Python concurrency. First, let me introduce myself. My name is Tawa, and I'm open source enthusiast. I was a MySQL developer before, and previously I was working for GE, IBM, Informex. Now I am a freelancer. I do corporate trainings and freelancing work. I have overall 18 years experience, and recently now I am becoming a Python addict. So in today's talk, mainly we will cover what are the concurrent programming idioms with what are the multi-threading concurrent programming, how do you do it in Python, what are the techniques, and understand its power and understand its limitations, and get a very high level understanding of the big picture with Python, right? It's a vast involved subject, so we are not going to gain a lot of minor details within 40 minutes session, but the idea is to get a very good high level picture, right? Okay, why Python? And we talk about concurrency, and we are saying Python, so it's not even a compiled language. So if you are that much performance sensitive, one might think I will write my application in C. Why do I write it in Python? But as a matter of fact, Python also has the CPython is a reference implementation of Python. It has something similar to your JVM. It executes your bytecode, and overall the performance of JVM is better than the Python virtual machine. That's for different reasons. A lot of resources have gone into JVM with the just-in-time compiler and all that. But having said that, Python is a language with a very high developer productivity, and scientific community loves it, right? And it's very easy to write a native extensions in Python compared to your Java or any other language, right? And if you take all this performance sensitive thing and write it in C, and Python is a very good glue language, right? So you write all the most performance sensitive things, you just write it in C and put it together. Python is a great language as a glue language. It's a scripting language, it's a general purpose language, so it's you can do anything, right? It's not like you are mainly meant for web programming or anything like that. So as a matter of fact, scientific community loves Python. So if you go to this scipy.org, so people do molecular, biological simulation, matrix multiplication, additions, your simulation, whatever you can imagine. Why? Because it's so easy to develop and put together something, rapid prototyping, exploring. It's amazing stuff, right? And and also there are native Python implementations, in the sense you can take your Python code and compile it to the machine language. So there is the PyPy, which does the just-in-time compiler, and also there is a Cython. So it is a slight extension of Python. You just give some type hints, then it converts your Python program to a C or C++ program, then it compiles it onto your native platform. So it becomes really as good as a C program. So you get to code in a very high level language. At the same time, you get to execute in a platform in a most efficient way, whatever you can imagine, right? It's like having a cake and you can eat it too. So this is why Python is really hot. Everybody loves it. And more than anything, as a glue language, also as a framework, you have to be aware of the concurrency limitations, right? So how it does the things because the concurrency is the centerpiece of attention, right? Because you put together these things, how this is going to exactly interact together. Is it an efficient way to do it, or is it okay? So you need to have very good high level, overview or a feel of it, how this piece works. All right. So now let us set some terminology. So we say concurrency and parallelism. So in general, there is a subtle difference between this terminology. So we define concurrency is something occurring at the same time. For example, I am typing my laptop or I am writing. So these two actions are concurrent. So I am typing for some time and writing for some time. But I am not doing writing and typing at the same time. So it's not really parallel, but these two things are concurrent. So when I say concurrent, it happens. It may be parallel or it may not be parallel. But when I say parallel, it's exactly parallel. So this is happening here, this is happening here, right? So that is a general terminology, that we'll use going forward. That's an accepted, fairly accepted terminology. So a multitasking is concurrent, right? So you do this for some time and you stop doing this, you do this for some time, then you stop doing this and you do it for some other time. So that's a concurrent thing. Okay. So let us review some very basic stuff. Yeah. Yeah, so what I meant is, if something is parallel, it is necessarily concurrent, in the sense like, some two things are going, so, two cars are, it's going in parallel. And that means it is necessarily, concurrent. Now, parallelism implies concurrency, but the concurrency does not imply parallelism. Okay. It's just a terminology. So, in general, you might mean synonymously. But for our discussion or in general, this is an accepted terminology. When we say concurrent, a multitasking is concurrent. But a parallelism, we mean real parallelism. Okay? Okay. So let us review some basic stuff, whatever we learned in our OS course. So we have the process, we have threads, and then we have processors. This is in Linux and even in Solaris. So basically, Linux has this concept of lightweight process. Say a lightweight process is something the OS knows about it. A process is something the OS knows about it. And a thread is something the OS may or may not know about it. So in the sense, a thread is typically, if you are writing a C program, you use a pthread library, right? So you say pthread create and all that stuff. Then basically most of the typical implementation, it makes a system call. So every pthread, the OS knows what a thread is, what your thread is, right? And typically, so if that is the implementation, then we say, it's the OS aware thread. So every thread may be directly bound to a lightweight process, or it can be loosely bound to a lightweight process. So your lightweight process takes up the thread and it runs it, and the OS knows about it, and the OS is the one which is scheduling your threads. So all those fun things are happening under the hood, right? But there is also another thing called user threads. So before some of the primitive applications or the most sophisticated applications, you may write a library to implement a thread, and the OS has no clue about it. So the OS might think it is a single thread, and it is a complete in library user space you can implement your threads. So it's called user threads. For example, you may think, whenever I execute a function routine F, it is thread 1. So whenever I execute this G, it is thread 2. it's your notion, right? You may think. Then, as I said, concurrency is also thread. So thread doesn't mean that it has to necessarily execute in parallel, right? So you do this for some time, F, and then from there, you jump, you do this in G, then you may think I'm executing 2 threads. It's your assumption, your notion, right? So you have your thread, so you run multiple threads. As a matter of fact, most of these databases like Oracle, Informatics, so they implement their own thread library. So that's what we call it as a cooperative multitasking. So they have their own thread library. Why do they have their own thread library? Is because it provides you exact deterministic behavior. Because you execute it for some time, then you want to do the thread switch. So you are not at the mercy of the OS. So if you are doing that, your database will run perfectly fine on Linux, but you will have a horrible performance on Solaris. So to avoid all that, so many of the databases and some of the high performance system, you may want to implement your own user level threads. And thread switching from one place to other, it doesn't happen arbitrarily. So you decide when to yield and when not to yield, right? So periodically in your program, you may call a yield. Then it will check if there is any other thread is running, then automatically it will jump there, right? So a simple mechanism of a thread could be as simple as you say function F1 is thread 1, function F2 is thread 2. Then periodically you call a function called yield. So whenever you call yield, so if F2 is ready to run, so you may jump there. Then then you after some time you call yield. Then you say, okay, now F1 is waiting for you. Then you jump, right? So this is how, at a very high level, at the library level, you can implement your threads. That's called user threads. Okay, so this is the very basic stuff. And let us see how this address space is laid out. So the left we have a single threaded system, and the right you have a multi-threaded system. So you have a single stack in a single threaded system, and if your process is multi-threaded, it shares your code, it shares your data, it shares your heap, but it has a different thread stack, right? So every thread has got a little bit of a thread stack. So so that is a very, very important concept. And conventionally, we also say that a stack has to be contiguous. Contiguous in the sense at the virtual memory level. So this is all virtual memory. I mean, it's not a physical frame. Your physical frame can be distributed. Yeah. So it is perfectly virtual. But even though it's a virtual, suppose you have 4 GB memory, right? So you may run out of virtual memory address space. Suppose you have too many threads, thousands of threads, 10,000s of threads, and every thread should have typically you don't know, you may be calling a recursive program, so you allocate 500 kilobytes or 1 megabytes, I don't know. So you allocate every thread a big stack. Yeah, no, okay. It doesn't matter whether I use a 3-dimensional or 2-dimensional, but the sum of all that, I'm running out of space. That's what I'm saying. So suppose I have 4 GB, right? And every thread, suppose you decide to allocate 1 megabyte, then I can at most have 4,000 threads, right? So 4,000 threads, each thread having 1 megabyte, your entire address space is gone. So nobody is really running. I mean, the physical memory is free. Maybe 3 GB is free, but you don't have the virtual address space, right? You can't even allocate it. So that's a problem. So, so just be aware that the concept of, so why do we have this, the stack has to be contiguous? Because of the simplicity, we always said that a stack is, it is contiguous. You make a function call, then you return back. When you return back, you pop the thing from the stack and jump there, right? It's a very fairly simple thing. But actually, every stack frame has to be contiguous. The entire stack need not be contiguous if you really think about it, right? So that's why, because all you need to do is you make a function call. When you return it, you go to some place and you take the return address and jump there. So that's all we need to do. So your stack could be a linked list, or it could be a tree. It could be anything. As long as you can traverse back and you know how to get back, it can be anything, right? So we will see that a stack having to be contiguous, it's a problem. It's a problem in the sense like sometimes it could be a problem for scaling, right? So we'll take a closer look at that later. Now that we'll just remember managing all this stack and thread stack can be a challenging thing, right? So this is how it looks, a single threaded thing and a multi-threaded thing. So let's say, a process, then we talked about the OS thread, which is basically a lightweight process. Then there is a user threads, we talked about that. And a process is costly, and OS threads is also not free. And the user threads is really good if you manage properly. I mean, because it's all your library routine, right? The OS, you don't even make a system call. You jump from one function call to another function call, then you can call that as a thread switching. So it cannot be faster than that, right? So if you manage the user threads properly, it is the most efficient thing you can imagine. Okay, so your pthread-c library creates the user space threads. So we use the terminology when we say user space, it is a user space versus the kernel space, right? So it is not the user threads. So when I say user thread, so not even the LWP coming into the picture, not even the pthread is coming to the picture. It's a completely a different library which maintains this, the so-called threads, right? So just we need to remember the OS threads can do a preemptive scheduling, and the user threads is a cooperative scheduling. A cooperative scheduling is little bit more difficult to program, but in the sense like you have to make sure you are yielding properly and all that, but it provides a deterministic behavior which is really good, and also the locking and deadlocking, all those things, analyzing it much easier because you have a fairly static deterministic behavior of the whole thing, because you know exactly when things are getting yielded, when things are getting switched and so on. Okay, so let's look at a life of a task. So you run for some time, there is an IO, then you run for some time, then there is an IO and all that stuff. So typically when the IO is happening, the OS takes the thread and puts it into the sleep, and the IO is happening between probably the direct memory access from your IO device, a file or whatever it is. So the CPU is not involved. So your file reading is taking place from the hard disk to the memory, and the CPU is just a spectator. So that is the time, if there is another thread is waiting, it can be scheduled. Okay, so a very quick refresher on the thread synchronization mechanisms. So threads use mutex locks, condition variables, and shared memory. So these are all the common primitives that we use to synchronize, and often a source of complexity and bugs. Suppose you have some 2 locks or 3 locks, even then you have to carefully analyze, okay, is there a deadlock? Can I lock this and I will never release it, so will it be a problem? So it kind of after if you do too many locks, it becomes like a nightmare. It's like a puzzle. Your whole program is like a difficult puzzle to solve, and there is some error handling, you return, some error happen without releasing the lock, so welcome to the deadlock. So then we use the message based communications. A message based communication is much more simpler in terms of a concept. Even for threads also, if you use it simplifies the whole thing, because every time you just imagine there is a message queue, You just put it and somebody else comes and takes it. So there is not the complexity is much better when you deal with messages. Then the processors use pipes and shared memory and sockets and so on. So if there is a distributed system, you have to use sockets, right? Because there is one machine here, then there is one machine here. They are remote. So the only way you communicate is by sockets. So now let us look at the Python threads. So this is how it looks. It's somewhat similar to your Java threads if you are familiar with Java. But you take any global function or whatever, then you create a thread. And by the way, Python doesn't have a new keyword. So whenever you want to create it, you just call that thread. Then you let it go, right? So then you say join, then it waits until the thread terminates. This is one version. There is also another version which looks more like your Java. So you define a class and inherit from the thread. Then you define a run method. Then you initiate that thread and you say run. Then the thread starts running, right? So this is how a typical a thread in Python looks like. So Python provides a fairly good amount of primitives for the synchronization. Whatever you can imagine, it is there. So what is the main difference between this and C? So most of these primitives you will see it provides a little bit of a higher abstraction. So in C you'll always messing up with the pointer, here bytes and here and there. So we'll see here a little bit of a better higher level abstraction. It's kind of a more pleasant to deal with, right? So we will see all that one by one. So lock and a re-entrant lock and semaphores and an event mechanism and a condition, right? Condition variable. So this is how a mutex lock look like. So you just say lock, you create a lock and you say acquire. Then your critical section, whatever you want to do, you can do. Then you can say release. So that is one way of doing it. Then later, fairly recently, Python introduced a with statement. So this is a more better way to do things compared to directly acquiring a lock. What the with does is that you say with a lock, then do something. So a lock or any other object, if it enters two primitives, something like a enter callback and a exit callback, enter and exit or whatever. I don't remember the exact name, but that's the functionality. It has to provide two callbacks. And whenever there is an exception which happens within the with call block, automatically it gets called. So you release whatever you want to do, you release it, and whenever you enter it, automatically the lock happens. So it's much more pleasant to use, more robust. So it's kind of preferred compared to the other lock. Okay, so then we have a reentrant lock. A reentrant lock is something like if you have a same thread, the same thread can lock it again and again. So that is a reentrant lock. Typically a mutex lock, if you already locked it, then you try to lock it, then it will be a problem, right? Why a reentrant lock would be needed? Suppose you are the process, you own it, and there are few routines. Then imagine a recursive call or recursive like call. You lock that object, you do something else, then that one recursively calls you back. Then you try to lock it. So basically you own, because you know what you are doing. You are the owner and you are the thread. And multiple times if you want to lock, you may want to let it go. I mean let it allow, right? But if you use a mutex lock, not only you have to remember you own it, but you have to remember who owns it, and it becomes kind of messy. So that's the time the reentrant lock will be useful. It allows you to lock the owner multiple times, but how many number of times you lock it, that many number of times you have to release it. Okay. Then we have.
Can I just take 30 seconds?
Yes.
There will be a feedback session right after this session. Here only. We would like you to be a part of it, so please be there. Everybody will come in. Thank you.
Okay. Yeah. Re-entrant lock. Yeah. So a re-entrant lock is suppose a thread locks an object, right? Where exactly it is useful? Okay. Suppose I have a class in which I define some 4-5 methods. Then whenever somebody calls that method, I lock it, right? Then those calls make other calls. So in general, every method does a lock, but there can be a chance that I call one method and that method calls another method. So I may try to lock twice. Okay, it's very common, right? So when I try to lock twice, if it is a mutual lock, then it won't allow you. If it is a re-entrant lock, it will allow you as long as the owner is same. So you can twice lock. A owner can lock it twice. Then the owner will have to remember it to release it twice, right? So it's a kind of more easier to program that way. Okay, so then the counting semaphore, it's a very common concept. So you can have a counting semaphore. Typically, if there are 5 resources or n resources, then you start with a n, and whenever the consumer, so the n represents the producer, and the resources is the n resources are there. So the consumer every time uses it, then they release it, so and so on, right? So this is so whenever you do an acquire, it is like a consuming. Whenever you release it, it's like producing. Okay, so then we have these events. So event it's a very small set of interface, but very efficient and useful. You can set an event to be true or clear it, or you can wait on a particular event, right? So e.wait, and whenever they set it, then you'll unblock, right? So this is the event, very simple, straightforward stuff. Then we have this condition variable. This condition variable is also a universal concept. It's the same thing in Python as well. The formatting got a little bit screwed up. I didn't get a chance to see the thing, but it's fine. So I'll explain it how it works. A condition variable is a combination of a lock and a signal. So you not only you say that a condition variable is always associated with a lock, right? So underlying a condition variable there is a lock. So so you can say, okay, until this thing is done, I am going to wait, right? So when you are waiting, you will just give up your lock, then wait. Then the other guy, so imagine there is a producer and the consumer. So they are strictly working in tandem. So this guy keeps producing and this guy keep consuming and go and so forth. So between this and this, we don't want to miss a beat. So if you use some kind of a lock, you release the lock, then you do an if condition, then you do something, then there is a race condition. So but if you want to coordinate these two guys, producer and consumer, condition variable is the way to go. So it's the same thing concept in C, in everywhere, right? So you say wait, then the other guy produces and they say notify, then you come back and all that stuff. Okay. Now, what are the common problems? So with all these threads and everything, deadlocks are easy to create. It is difficult to debug. Then it is a non-deterministic scheduling, which brings its own challenges. It's a source of lost sleep. Okay. Now, we also have queues. Python provides you with the queues. It is whatever you will imagine. You initialize a queue, you put an item, and you get it, and you can check whether the queue is empty or full. So as I said, working with queues is much more pleasant experience compared with working with logs and stuff, right? So it's whenever you can, so it's simpler and easier to use. Okay, so then Python threads performance. Let us see. Interestingly, Python performance on CPU bound threads is bad. Bad in the sense, like I'm referring to the C Python, which is a Python reference implementation. So if you have two CPU bound tasks, so you try to use thread, it runs more slowly than a sequential execution of the two threads. So you suppose you have a CPU bound task for 1 second and another CPU bound task for 2 seconds. You use threads, then you are going to take more than 2 seconds, which is unfortunate because the reason for that is because the Python uses a global interpreter lock in the standard reference implementation, which doesn't let you to execute two Python byte code at the same time. So basically it it makes your entire flow sequential. So you are not really gaining anything. But however, most of our program is IO bound. So your IO bound tasks are perfectly fine. So it's not that threads are necessarily evil in Python. It's okay, but this is something you have to remember. And as a matter of fact, JVM doesn't do that. So your Java JVM, which has got threading, really did it very well from the bottom up. So it was designed well. It is a true concurrency. Even JVM initially they had these user level threads. Then later nowadays every JVM implements the native threads. Okay, so this is the CPU bound threads. It's an example, so which illustrates you do it sequentially, then you measure the time, then you do it in parallel using threads and you measure it. You will find that using threads it executes slower. Then we talk about so I'll try to speed up a little bit because we don't have much time. So the global interpreter lock, it talks about why it is there. It is there because it makes your implementation easier, and native extensions are easy to write. It's a kind of an excuse. We have to fix it, and the GIL is not a global problem. And there are implementation of Python which doesn't have this problem. Interestingly, a Windows implementation doesn't have this problem, the Iron Python, and also there is a Jython. Jython is a implementation which compiles your Python code into JVM, and also all your Java libraries is available in Jython. So Jython doesn't have this problem of global interpreter lock. So basically, if you want to leverage all the CPUs, it's a well-known mechanism is that you have few CPU, processes running, and every process runs as many threads as possible. So if you want to get a maximum out of a 4-processor machine, typically you run some 4 processes and bind these processes to a processor, and that process itself runs in multiple threads in parallel. So that is an idea. Typically you want this combination of process and threads to squeeze maximum out of your hardware. Yeah. No, the CPU, the Python doesn't provide any kind of an API to say that I want to bind to this CPU. No, it doesn't provide this API. Okay, but you will see that in Python we have some other approach in which we can really write a very efficient program. So you will see that. So threading, we said it's a kind of not really good, but there are a lot of high-level abstractions Python offers, which makes your multi-thread programming really a breeze. So Python allows you to to serialize your object, and it's it's very simple in a couple of calls. Then the Python provides you very high level IPC mechanisms like a pipe, sockets, libraries, and so on. Then process handling is really good with Python, because we know most of the time threads is not that efficient. Then you have these libraries to deal with process. You can almost treat a process like a thread. I mean, you can create a process pool, you can join and wait for the process to die, and a lot of these abstractions are very easy to use. So there is a multi-processing module. So there is you can almost treat the process like a thread. Then there is a pipes. So a pipe in Python and a pipe in Unix and C, the main difference is that a pipe is like a byte stream. It's a stream in C program. But in Python, it allows you to have a little bit higher abstraction. It's an object. So even though it's a pipe, you put the objects, and when you receive it, you read the objects, which is kind of much better to use. And of course, you have message queues in Python. Then we have, as I mentioned briefly, we have a process pool, like a thread pool. You can have a process pool and get the things done. Okay, so now we are getting more to the more interesting part of the talk. So when you want to do something, more efficiently, there are mainly few approaches. How do you do it? A thread, how this, that. So there are mainly 2 or 3 different approaches. One is the event-driven asynchronous approach, which involves a callback, and another one is a cooperative multitasking, which is called coroutines. Coroutine is similar to subroutine, but the 2 routines are like a pairs. They are not, one is not the sub of the other. So the both are like a pair. So it's a very powerful concept. It's not a very new. It has existed in many other languages before, but none of the mainstream languages have it. So and it's a wonderful concept. That you will see in a more other examples. Then there is another model called actors-based model, in which everything is an actors. They communicate through messages. So this is also a very good concept, which kind of simplifies your entire approach of the designing the complex system. Okay, so asyncore is a module in Python which lets you to do an asynchronous level program. It is a very small networking library. Basically allows you to write an asynchronous. You provide a set of callbacks. When something is done, your callbacks is executed. It's as simple as that. It's a very minimal library, a core library, which allows you to write a program in an asynchronous style. Then you welcome to the world of coroutines. Coroutines is a very powerful concept, very modern approach to write a parallelism in your entire logic. It is like subroutines, as I mentioned, but at a pair level. So this is how it looks like. So the entire coroutine, really a single thread of execution executes 2 routines. So roughly speaking, a coroutine is a mechanism in which you can have a go-to across functions. So typically, your C program or no program allows go-to across function calls, right? So it's a roughly speaking, a coroutine is a mechanism in which, so if you are familiar with a C, there is a set jump, long jump, and all that. But the set jump, long jump is a system call. It is costly, right? But this one, it is almost like a user level. You from here you make a jump there. Now you count down. So countdown, if you see, it is a function which yields an integers, right? Then you use that function as an iterator within your for loop. So when I say for x in this function call, that function call returns an iterator. That iterator starts producing an integer. So now since I have a while loop, basically that function will keep on producing the integers until the n reaches 0, right? So we call such a function as a generator because it generates a sequence of numbers. So very simple concept, but it is so powerful. It's very, very powerful, right? So why it is powerful? Because you make a function call and the function returns a value, but it preserves the state. Next time you ask that function, give me another value, it just continues from where it left off, right? So you can re-enter the function multiple times and it remembers exactly where it was before, and from there it continues. So it's a kind of making an arbitrary jumps across function call. So that is why it's so powerful and so cool. So when you have a generator, typically there is a kind of a parent-child relationship. So a parent is a caller and the child is the guy who is generating it, right? Then later what they did, they mailed the yield statement as an yield expression. So we'll see an example and that will be easier. So if you see, this is a coroutine, because earlier if you do a ping is a function, it is like a generator, but it's a generator which returns the yield statement, returns a value. So what does that mean? That means you can have a two-way communication between your generator and a caller. So far the caller calls the generator and the other guy gives only one value. But in coroutine, you can also give a value. So you get a value, then you send some value, then the coroutine produces another value. So almost a conversation is taking place between two coroutines, right? So that is a very rough concept, but it's a very powerful concept, right? So there are amazing things you can do with coroutines. You can create a pipeline of tasks. You can create filters. You can create a tree-like broadcast pipeline. You can implement a state machine, because from this state to that state to that state, you can implement a state machine. It is somewhat similar to your object-oriented programming, but it does it more simpler. And most importantly, it provides you a deterministic control flow. You are not at the mercy of the operating system or anyone. And also, since you know exactly how the control flows through, most of the time you can get away without using any locks at all. Because from here to here, that's how I jump, and I don't really need any lock, right? Okay, so now we saw there are 2-3 different ways of approaching a problem: a synchronous, asynchronous, a coroutine, and all the stuff, right? So let us see, which one is better. So the classical example, you take an Apache. Apache uses a process and set of threads. Then you look at the Nginx. Nginx is the high performance. It's a reverse proxy first, and also it's a web server. So Nginx uses an asynchronous model, an asynchronous callback model, right? And Nginx scales far better than Apache. There is no comparison, right? So that is why asynchronous model is the one to go with. It's very efficient, it's wonderful. If you are thinking in terms of threads, and often asynchronous model is the right way to go if you really want to scale, right? But you are not worried about scaling. Then most of the time just look at your program, whatever is conceptually simpler, you just go with that, right? So we are not going to complicate our life just because one technology is better than the other technology, but we always look at the problem on the hand, right? Okay, so when all these web servers came, there was this famous C10K problem. What is the C10K problem? It is like a concurrent 10,000 web server connections problem. So for the goal of these web servers, how do I serve 10,000 concurrent connections, right? So it was not possible at that time. Now it is possible. Now we can have even your laptop with a slightly higher end model, so you can serve 10,000 threads connections at a time. So we have come very far. So the asynchronous programming. So non-blocking with callbacks is the theme, and so you do select poll or KQ or whatever is the most efficient on your operating system. You can use that. Then there is something called a stackless Python. A stackless Python is the one variation of a Python implementation in which they don't use interpreter stacks to execute your Python threads. I mean Python code, right? So it so happens that the Python reference implementation, when it executes the Python logic, it uses the interpreter stack. So which creates a problem in your scaling, right? So your stackless Python implementation removes that logic. So it uses a separate heap for the stack of the user threads. So that's why it scales really well. It's a very interesting concept, very deep. So we cannot go deep on that. So I'll skip over. It's just to good to remember there is such an implementation which exists. So this is the synchronous task, and this is the asynchronous task. So you keep on getting a callback. It's the one thread of execution. And then stackless is the, as I said, it's an implementation in which the Python threads does not use the interpreter stack. It uses another stack or a heap. So what the CPython reference implementation guys have done, they have taken a subset of the stackless Python implementation and they merged it to the CPython, which is called Greenlet. The Greenlet is a very lightweight thread, which is very good for scaling, right? So that the Greenlet is a very good thing to do, very good thing to use. Then the Burst Python asynchronous framework. Okay, so these are the framework library, the very well-known framework library used with Python. There is a Twisted. It's almost like a de facto standard. So the most famous one. And there is a Tornado, which is used by Facebook. It feeds the Friend Finder website. Then there is a G event, which uses Greenlet underneath. It's basically a lib event based high performance network library, right? And there is a Concurrency, there is a Circuits, then a Diesel Web, and there is a Cogent, right? So each one is very interesting on its own way. So, but as you take a look, Python provides a very rich varieties of framework, which are very interesting to look at. So G event, so we are running out of time, so I'm just skipping it. It's one of the very modern framework, very good. So Twisted is a de facto, and Tornado is a very fast one. The Actor model is a very popular framework. Aka is a framework in Scala, and there is a corresponding Pyka in Python, which implements a very small subset of Aka framework. Okay, so now we have to finish now, and all this slide is available on my website. It is in zatvia.com, so you can look at it later. All right, so okay, perfect. So you have to just remember zatvia.com. You can access the slides. Yeah, I'll upload it.